Okay, so last class we left off and we were looking at, let me see here, I don't have a blank one, the binomial distribution, and what we said was that we can do it in Excel, and kind of the way that I had finished class kind of showing you was that we need three things for the binomial distribution, right? The number of trials, the number of successes we're looking for, and the probability of success, right? So I think the example I had was like, we're looking at 100 people. The probability any one person is a millionaire in the United States is 0.067, right? Or 6.7%. Okay? We could be interested in finding maybe, let's say, exactly 5 people out of those 100 are millionaires. So we go over here. Think about this is the probability that x is equal to 5. And we'll use that, whoops, not a negative sign, an equality sign. So binom.dist. The kind of format we needed was the number of successes, which we have here, comma, number of trials, which is in that cell, and then comma, the probability of success. We then said, comma, the last thing we need to tell is whether or not this is cumulative. So it says you can put true or false. 1 is true, 0 is false, so we'll put a 0, right? We don't want this to be cumulative. We just want the probability that x is equal to 5, okay? So what Excel will do is basically use those three things and plug them into, where do we have it? Somewhere back here. Well, that's not the general form of the equation. I wanted to show you. There it is. Plug them into this equation for you, okay? So that's what Excel is doing behind the scenes. So we hit enter, and it spits out at me what that probability is. So one thing we could do is start to think about, so 0, 1, 2, 3. Think about different numbers of successes. Right? Oops. Let's move this down one. And if I right click and kind of come down here, and I go to fill series, it'll kind of go up by 1 for me. So what I could do is, maybe I'm interested in like the number of millionaires I'm going to find, because maybe I'm trying to look for some backing for some project, and so I want to know what's the probability if I ask 100 people, I end up getting 0 people or 1 or 2. So we could find all those different probabilities pretty quickly in Excel, because I've got my number of successes I'm interested here on the left, comma the number of trials up here, comma the probability of success, and then once again, comma 0, because I don't want to make it cumulative. I just want the probability that x is equal to 0. Now, when I copy this down, I want the number of successes that cell reference to update. But I'm still looking out of the same number of people, right? The same 100 people, and the probability that any one person has is a millionaire hasn't changed. So I'll highlight those two references, hit F4 or FNF4, or on a Mac command T. It'll put those $signs and freeze those cell references for me, so that when I copy this down, right, now I get the probability of all of these different numbers of outcomes. Okay? Any questions on that before I keep moving? I have an eye on the chat here. Okay. So the next thing we're going to think about is, well, first of all, I want to point one thing out here. If we wanted to calculate the mean, we said that was simply the number of trials times the probability of success. So here we've got the number of trials multiplied by the probability of success. So the mean here, right, the average number of people out of 100 who will be millionaires, based off of this percentage, is 6.7 people. Right? So we said last class, if we find a mean that's not an integer, that means, well, we can't see 6.7, people. We only see 6 or we see 7. But what this is telling us is that 6 and 7 should be the most likely outcomes, right? And if we look at these probabilities here, sure enough, these are the two highest for the value of 6 and 7. And then as we move away from that value of 6.7, the probabilities decrease for those, different numbers of successes. If we even wanted to, we can kind of see that visually if I just graph these probabilities. So I highlight the probabilities and go to insert a column chart here. Kind of shows me that the two, oh, it's because here's the problem. So if we're trying to graph these, not that I probably won't ask you to do this in Excel, but the problem is it always starts at 1, but our number of successes actually start at 0 here. So I'm just going to right click on these numbers. We'll edit the axis labels so that we'll use the number of successes we had over here, okay? So you can see that 6 and 7 are the most likely outcomes. And then as you move away from those values, right, that middle point of 6.7, the probabilities decline, right? So that's kind of a nice visual for us. I'll get rid of this, though. I don't want this to be here for right now. So I'm going to move this down over here. So what if instead, let's say I want to find the probability that x is less than or equal to 6. Okay? So I want the probability that x is less than or equal to 6. Well, if I have already if I've already done all this work, I could just say, well, all I'm going to do is add up the probabilities of every outcome that meets this criteria. So the probability of 6 plus the probability of 7, or sorry, probability of 6 plus the probability of 5 plus the probability of 4, all the way down to 0. Right? So I could just use that sum function and add up these probabilities. Right? So once I do that, I get my answer. But there's also another way I can do this in Excel, even if I didn't have, if I didn't already have all this work done. Let's say I even started from a blank sheet. I could say, okay, take the number of successes I'm interested in kind of, if I'm trying to find a range, right, x is less than or equal to 6, use the highest point there, so 6, comma, the number of trials is 100, comma, the probability of success is 0.067. And now instead of a 0, for cumulative, we put a 1, right? Remember, cumulative is start at this point and add up everything below it. So take the probability of 6 and add to that the probability of everything below it, right? So making that a 1 tells Excel to do that, right? If we were doing this by hand, we'd have to take the binomial function, find the probability of 6 using that formula, then find the probability of 5, then find the probability of 4, all the way down to 0, and then add them all up. Well, that's essentially what Excel is going to do behind the scenes for us when we tell it to make this cumulative. And sure enough, we get that exact same answer as if we would have done all the work ourselves and then just added up those first, 7 probabilities here. Okay. So that cumulative option is really nice in Excel for binomial distribution problems. However, what if we want to do the probability x is greater than or equal to 8? I think this is the value I use in the slide. Well, if we think about here, this is our event A, right? X being greater than or equal to 8. Okay. So A complement would be that x is less than 8. Right? And we know that if we want to find the probability of an event, we can just set that equal to 1 minus its complement. So if we think about what the complement would be here, that would be that x is simply less than 8. But we have to be careful, because if I say, all right, I'll just take 1 minus, and then here I've got a cumulative, right? Just like up here, we have a cumulative binomial distribution we could use, distribution function we could use to find this, right? But if so I use that binom and I say, okay, start at 8, number of trials I have is 100, probability of success is 0.067, and I want to make it cumulative. Right? So what's going to be the problem with this, right? Well, I am doing 1 minus, right, the complement. The problem is the complement is being less than 8. Remember, when I use this binomial distribution function and I put an 8 in here, that means it first finds the probability of 8 and adds up to that every probability below it. So this would actually include 8, and I don't want to include 8 here, right? There's not an equality on that complement that I came up with. So instead of putting an 8 here, what's the very first outcome that actually fits the criteria of this probability here? Remember, we're dealing with a discrete variable, so the very first outcome that is less than 8 would be 7, right? So it gets a little bit tricky there when we want to kind of use this complement rule and use this binomial distribution function where I've got this kind of cumulative idea going on here. Because if I don't have an equality on that complement, I need to make sure, like, yeah, this is x is less than 8, but that means I don't want to put an 8 into the function. I actually want to put in the very first outcome that fits this criteria, which is actually a 7. Okay? So if I do that, right, we'll kind of end up with the probability that x is greater than or equal to 8. Okay? Any questions on that, or want to see one of these cells again? Or so this is, you know, be careful when you're kind of using that complement rule in Excel. It can get a little bit tricky there. Okay. Now, what if we have? I'll go through another one just to do it real quick. So what if I had probably that x is what do I want? Greater than, I don't know. We'll do 10. Right. Well, once again, like, I don't want to actually find the probability x is equal to 11 plus the probability x is equal to 12 plus the probability x is equal to 13 all the way up to 100. Right? That seems a little crazy. And unfortunately, that binomial distribution function in Excel doesn't have an option for kind of looking above a certain value. So if this is my event A complement would be less than or equal to 10. And now this one becomes a little bit easier, right? So now if I'm thinking about how do I find this complement and subtract it from 1, well, it's just that binom.dist. But now, because the equality is on that, I can actually just use that value of 10, right? Comma, number of trials, comma, probability of success. And then we're making it cumulative because we want the probability that x is less than or equal to 10. Okay? And that's how we do that. All right. Any questions on that? There's one more thing I want to show you in Excel before we move on. Just wait to see if there's any questions. Okay. So we will, I'm just going to copy this down. I could actually get what the very highest outcome we could see is that 100 out of the, whoops, I probably went too far. Yeah, 100 out of 100 people that we ask are millionaires. Oops. A little bit too far here. There we go. Notice anything past that number of trials was giving me an error. So the probability that if I asked 100 random people that all 100 of them are millionaires is 4e to the negative 118, which means this e means move the decimal point 118 places to the left, right? So 117 zeros and then a 4, right? So pretty much 0, right? And you'll notice all these, anytime we're moving that decimal, 20 places to the left, all these probabilities are essentially 0 until we get to about 17. Because think about it, I mean, if on average 6.7 of the 100 people are millionaires, what's the probability 17 are? Well, pretty unlikely, right? A pretty low probability. If on average 6.7 of the 100 people would be millionaires, then the values around 6, 7, 5, 8, those are going to be our most likely outcomes. Okay. All right, so I'll even go ahead and save this, and I'll post it after class. Right. So if you kind of want to take another look at this, it'll be up there on Canvas. So the next distribution we'll talk about here we go, is the Poisson distribution. Okay. So I think last class, right before we talked about Excel, we went over these kind of different scenarios, which of these was not appropriate. And the one that we kind of selected was this one where we're looking at the Muncie Airport. And the reason why was because it was over a period of time. So I said, we might have another distribution that is better with dealing with that. And in fact, we do. It's the Poisson distribution. Okay. So this is still a discrete random variable. It just follows a different distribution. And we're still looking for the number of successes. But we're now looking for the number of successes, or the probability that something occurs, over equally lengthed intervals, right? Now, equally lengthed intervals, typically, almost all the examples that we'll be thinking about, I'll show you one or two that aren't time, but any example I give you, like on an exam, or if you look at the practice exams, I'll always give you examples of time there, right? So what we're really thinking about is, we can set up what this needs to be true. I'll never kind of violate any of these principles where, you know, we have to be that every interval that we're looking at is independent from another, and it's, you know, they don't overlap. What we're really thinking about with the Poisson is how many times does something occur, or what's the probability that we see something occur a certain number of times over the next week? Or what's the number, you know, to give you a couple examples, you know, what's the probability that next week there are 3 accidents on McGalliard over that entire week? Or what's the probability that there's 2 accidents on McGalliard over the next week? You know, you could, you know, keep going with that and find the probability of any different number of successes there that you're interested in. Okay? So just like the binomial distribution, we're going to have a probability mass function for the Poisson distribution. Okay? So here, right, what are some things we might not know? Well, we've already talked about the factorial, right? So we know how to deal with that. We've got this lambda here, this Greek letter. All that is the average number of occurrences we typically see. So, you know, if on average there are 5 accidents on McGalliard every week, our lambda would be 5. And then if we wanted to know, well, what's the probability that we see only 3 this week, our x would be 3. Okay? And really that's all we need. Once we plug lambda in, once we plug x in, we're done. Because this e here is just some natural kind of number that occurs quite often in nature. It's kind of like pi, right? It's a number like pi, right? So if you can't find it in your calculator, I know every calculator should have this. Sometimes you have to hit like second, and then it's on, you know, one of the buttons. But if you don't, you know, for whatever reason you couldn't find it, 2.71828 right out to the 5th decimal is what this natural number e is that we could plug in there. Okay. So, you know, just like the binomial told us, the probability that we see a certain number of successes out of a certain number of trials, this probability mass function is going to tell us the probability to see a certain number of occurrences over a given time interval, right? Or really, it doesn't have to be time, but like I said, I'll almost, you know, the examples I'll give you will be time examples. Okay. So let's think about kind of a setup example. So this guy, I'm going to try to say his name. He wrote this book, pretty influential in mathematics, The Law of Small Numbers. And what he was noticing was, you know, one of the examples that he kind of gives, motivating examples he gives in the book, is that on average, about 0.61 soldiers were getting killed by getting kicked by a horse in the Prussian cavalry every year, right? So our time interval is a year, and our lambda, right, on average, we're seeing 0.61 soldiers die. Well, what's the probability that I would see 3 soldiers die this year? Right? So the number of occurrences I'm interested in x is 3. The average I usually see lambda is 0.61. That's all I need. Right? Those are the only 2 things that I need to then plug in to this probability mass function. Okay. So, you know, once we have our numbers plugged in, this really becomes like just a matter of getting this entered into our calculator. Right? Any questions on that? Okay. So if we go ahead and plug that in, pretty low probability, right? If the average is typically 0.61, the probability we see 3, that's, you know, moving away from that average, that probability is relatively low. Okay. So the same sort of thing. Let's see if I can get this. Hopefully, maybe it's sleeping a while. Well, it's still not picking it up. Okay. So how can I think about doing this? So this isn't going to be perfect, but bear with me. So if we're thinking about just like the binomial distribution, if we look at, and here, think of the smallest number of soldiers I could see getting killed are 0. Why is this so big? Because I have it set really big. It's too small. All right, we'll go with that. And then we'll move this over here for now. Okay, so I've got on my x-axis the value of 0, the value of 1, value of 2, 3. We can keep going if we want to. So we could use this equation plug in x is equal to 0 and get a probability. Plug in x is equal to 1 and get a probability. So what's going to be true is that, just like the binomial, wherever the mean is, right, the mean here, we're directly given to it. The mean number of soldiers we see getting killed is 0.61. So that means that 0 and 1 will be our most likely outcomes. Right? As we move away from that average of 0.61, our probabilities, right, start to decline. So if we're just kind of using these bars to graph these probabilities, right, as we move away from 0.61, these start to rapidly decline. Right? So the same kind of principles apply to the Poisson as the binomial, right? I guess, finding the mean's a little bit easier here because we're always given what the mean is, right? We don't have to take n times p, we're just given what that mean is, okay? Any questions on that before I keep moving, or I move on and get rid of this here? All right. Excuse me. So another example, just to kind of get some ideas here and see it in a different way. Let's say a hospital is worried about staffing, right? Having enough staff to deal with the number of births they are going to typically see. So on average, they see every hour about 1.25 births, right? They look at some historical data and figure out that's what the average usually is every hour. Well, what's the probability we're going to be understaffed, right? And that in this next hour, we see exactly 3 births, right? So we might want to know, because if the probability of higher numbers of births starts to increase quite a bit, we might want to make sure we have more people on staff to deal with that. So what's the probability that exactly 3 occur in the next hour? Well, there we're given the average rate, right, 1.25. We want to find the probability that x is equal to 3, right? So we've got our lambda, our average rate, right, 1.25. The number of successes we're interested in 3. It's a matter of plugging those into our equation, right? We plug in lambda, we plug in x, we're good to go. Okay. So if we do that, we get about what, a 9% chance, or a probability of 0.09. So here, right, I would get comfortable with, once again, making sure you can find that factorial button on your calculator. It's going to be really important for both the binomial and the Poisson distribution examples that we use. Also, finding that natural kind of number e on your calculator will be important as well. But really, I mean, once we identify the pieces we need, it's just a matter of plugging these into our equation and getting it entered into our calculator. Okay. All right. So this is the one where it might get a little tricky because I don't have anything to draw for you here except for on the screen. So what if we have that same type of example at the hospital, but we want to know what's the probability there's 2 or more births? Well, this starts to become a problem, right? Because if I think about what I'm wanting to find, I want the probability that x is what, greater than or equal to 2. So, and excuse my notation here, greater than or equal to sign, instead of like trying to find this image, I'm just writing it like we would have to write it in Excel, since hopefully we're kind of getting familiar with that. So the probability that x is greater than or equal to 2, well, what are the outcomes that fit that criteria? So x could be 2, x could be 3, x could be 4, right? And we basically would have to keep going, and when would we stop? Never, right? Because we're looking at a time interval. Theoretically, you could see, I guess maybe it's capped at the number of, women within a certain age range in wherever, the city or county that this hospital is in. But really, like, where would we stop? And even if it was like we finally do stop at a really large number, I don't want to use that Poisson distribution that many times, right? So very similar to the binomial, if we run into a situation like that, it's probably better, right? If we think about probably x is greater than or equal to 2, that's going to be equal to 1 minus its complement, right? So what would the complement of x being greater than or equal to 2 be? Well, that's just that x is less than 2. What are the only outcomes, right? I think about here. what are the only outcomes that fit this criteria? If x has to be less than 2, x could only be 1. Oh, running off on it. There we go. There we go. X could be 1, or x could be, no, sorry, x could be 0. All right? I'm having trouble typing right now. So if I want the probability of an event, and it's like greater than a certain number, and it's a Poisson distribution, there's no way I can find this, doing it by adding up the probabilities of every outcome that fits this criteria. I can find it by taking 1 minus its complement, right? So, now I only have to use that Poisson distribution equation 2 times. Once where x is equal to 1, once where x is equal to 0, add them up, and then subtract that from 1, okay? Now, before we I think I have that on the next slide, but if we just think about these answers for a second, what will be the 2 most likely outcomes if my average rate is 1.25? Well, that means my 2 most likely outcomes will be I see 1 or 2 births every hour. Right? Those should be my 2 most likely outcomes. Okay? One of those outcomes, is in that range of being greater than or equal to 2. Okay? Not only does it include one of the 2 most likely outcomes, it also includes almost all of the other outcomes, right? The only outcomes that don't fit this criteria were when x was equal to 1 and x was equal to 0. So I don't know exactly where this probability is going to be, but I'm probably guessing it's almost for sure going to be greater than 0.038. If it includes one of the 2 most likely outcomes and then almost all of the other outcomes, it's probably going to be a fairly high number, quite a bit higher than 0.038. Okay? So, oops, exit, there we go. So we kind of already have talked about this. All right, we keep going. Plug these, x is equal to 0, x is equal to 1 in. We then subtract those from 1, and we get about 0.355. So it might not be as large as we expected, but it is still quite, it's not 0.03, right? Any questions on this? Because I kind of had typed on the other slide as we were working through, but here's kind of the actual math when we just plug these values in. Now, one thing to remember, he's not here today, but he checked me on this. I could see him last class and he was here. Anything to the 0 power is going to be 1. Right? You can try that in your calculator. Anything to the 0 power is a 1, and 0 factorial will always be 1. Okay? So those 2 things kind of simplify here to kind of make this equation a little bit easier if you're entering it in your calculator. 1 times anything or anything divided by 1 doesn't change it. So you really could just think about this is what e to the negative 1.25 is. Okay? Excuse me. Any questions on that before? Where's the chat? There it is. We keep moving. We're okay with this? Everything's sounding okay, hopefully. All right. So I'll give you some visuals, right? How we can think about different Poisson distributions. Because remember last class, I showed you a similar thing where we thought about, you can see different shapes of the binomial distribution as well. Okay? So if we looked at Poisson distributions with really low means, right, like 0.1 or 0.5, well, that means that 0 is going to be the most likely outcome in those scenarios, right? And then as we move away from those means, the probability of seeing higher number of occurrences over that given time interval start to decline. Okay? As the mean gets higher, right, moving from like 0.5 to 2 to 5, kind of notice you get this kind of shift in the Poisson distribution to where the most likely outcomes, right, start to move to the right, and you start to get some number of occurrences that you can see to the left here. And it's kind of becoming like less and less right skewed to where eventually if you kind of got, a large enough kind of mean, it might start to look a little bit more like a normal distribution. Right? But this is kind of the general idea. But we can still see, even when the mean is 5, right? The most likely outcome is 5, and then as we move in either direction, those probabilities start to decline. Right? And this intuitively makes sense, right? If on average there are, I'll go back to the trap, like there's 5 accidents on the Galliard every week, Well, what's the probability that you see 100 this week? Well, very, very low, right? That number of occurrences would be very, very far away from the mean, right? But the values that are near the mean, those should be pretty likely to occur, right? We're going to probably see something around what that mean value is. Okay. All right. So this goes, this is just kind of a making sure we cross our I's dot our I's and cross our T's. So I've already kind of said the mean is going to be that lambda, right? We're going to have to be given that in the problem. We're going to have to know what the average rate of occurrences over the given interval is from whatever problem we're working on. So we're always going to have the mean. But kind of a weird property of the Poisson distribution is that the mean is actually also equal to the variance, right? So actually the proof on this one's a little bit tough. So you can, if you look at the mathematical proof on this, it doesn't matter. You can go ahead and think about, well, if lambda is the mean, then I take my different number of occurrences. So 0 minus the mean squared plus 1 minus the mean squared, and then each time you have to multiply by the probability that you saw 0 and multiply the probability you see 1. You can work out that the variance and kind of prove mathematically that the variance will always be lambda. So it's just a really weird, kind of nice property of this Poisson distribution. And then, of course, the standard deviation, just like always, we just take the square root of the variance, right? So just the square root of lambda here. Okay. Any questions on that? Okay. Yeah, so this is kind of a nice little property that Poisson has. Do I want to go through this with? I'll go through this example. I'll probably post a short little video of me working through this by hand, but we'll kind of work through it using the slides and maybe Excel and maybe some kind of the Zoom writing tool. So let's say we go back and think about the binomial distribution for a second. So let's say I've got 10,000 atoms. So this is going to be kind of not really a little bit different of an example than I would typically give you like on the exam or something. So let's say we've got 10,000 atoms of this substance. The probability any atom decays over a 1 minute time period is 0.0005. Okay? So what's the probability that exactly 3 atoms decay in a given minute? Well, I've got 10,000 atoms. The probability any 1 atom decays is 0.005. And I want to know what's the probability that 3 atoms decay. So because I do have, right, a cap, right, or a number of trials I'm thinking about here, I could use that binomial distribution, right? Plug in x is equal to 3. Plug in n is equal to 10,000. My probability of success is 0.0005, and I could figure out what this is. Now I have to do a little bit of a trick here, right? we're going to have to cancel things out. My calculator can't do 10,000 factorial, but everything from 9,997 and below will all cancel, right? So I can figure out what this probability is, but it's kind of annoying, right? I have to write out those factorials, even 10,000 times, 9,999 times 9,998. It's a pretty big number, like to deal with in my calculator. This is kind of not, not fun, right? So the factorials are annoying. Anything about, even if like, let's say I want, probably that 10 atoms decay, potentially if my n is too large, right, I might even run into problems with my calculator here. Okay? So anytime we have a really, really large number of trials and that probability of success is relatively small, the number of successes will actually follow, like that binomial, the shape of it will actually look very close to a Poisson distribution. Okay? So what we can do, and I'm showing you this more because it's interesting to relate the two. I'm not going to expect you to be able to do this on the exam, but I could convert my binomial. I'll just take the binomial mean, so n times p, and I'll set lambda equal to that, okay? Now I'll just treat it like a Poisson distribution. So, if we do this fancy kind of math proof, we can show that the binomial will actually approximately be a Poisson distribution. So in our example, the number of trials we had was 10,000. The probability of success was 0.0005. So we get our mean of 5. I then said, well, what's the probability that 3 decay in the next minute? So X is 3. I can solve this pretty easily, right? If I see here, if I compute this, it's 0.14037, and what? The other one was the same exact thing out to the 5th decimal. Now, if you go out to, a far enough decimal place, these will be a little bit different, but it's a really good approximation if you have a really large number of trials and a really low probability of success. So this isn't perfect, but even if we look at, notice, so here's my Poisson when the probability is 0.1, relatively low. If we go back to last class, where is it? Somewhere up here. Notice it looks kind of similar to a binomial when the probability is relatively low. So, but once we kind of get higher probabilities, these start to look nothing like our where are they here? Our Poisson distributions. Okay, so we can approximate only if we've got these really large number of trials, like 10,000, and a really low probability of success, like 0.0005. Like I said, I won't ever ask you a question where I'm expecting you to make this conversion. I'm just kind of making you aware that it exists. Because, what is large enough, and what is a low enough probability? Well, we could actually come up with, a bounds for how far off we want the approximation to be, but we're going to punt on that and not do any of that. So we're just kind of introducing this and making you aware of this idea. Okay? So let's talk through a few possible scenarios for our Poisson distribution, kind of like we did last class with the binomial. So let's think about which of the following is not going to be like a correct situation where we can apply the Poisson distribution. So the probability of number of accidents occur on a highway on a given day. Well, I've kind of used this example, so that one makes sense, right? If we had the average number we typically see, this would be a really, really good one to use the Poisson. The probability of stock return exceeds 10% in a given year. Well, we've got a time period, but what's the probability it exceeds 10%? Well, is 10% like a number of occurrences, or is the average? This doesn't really even apply to any type of discrete random variable we've been talking about, because we've been looking at the number of successes or a number of occurrences, not kind of the percent return. That doesn't really make sense for us with the Poisson, right? So this is going to be the one that we can't use the Poisson for. What about the other ones, though? We can think about the probably a certain number of calls to a call center, well, in a given minute. So we've got that time interval. We're looking for the number of calls. Perfect. I put period of time here. It could be a month, could be a year, but they probably have a certain number of insurance claims. Or we're looking for the probability of a certain number of occurrences. That basically is the Poisson distribution. Probability of a certain number of occurrences over a given time interval. Okay. Excuse me. Now we could I'll give you an example because I don't think I have any here. This one's kind of an example, but I'll give you an example of one that isn't a time interval. You could do something like, what's the probability if I'm walking, I don't know, walking down McGalley or Tillotson, one of these roads, what's the probability I see 5 pieces of trash on the side of the road, right? Well, there's no time interval there. I'm actually thinking about, and I shouldn't say on the side of the road, what's the probability I see 5 pieces of trash over the next mile, right? I could make it like distance intervals. We could use the Poisson, or kind of we could look at like volume intervals, and that's kind of the next example that I'll walk through, okay? So there was, I forget his first name now, but W.S. Cassette, right, was this guy, and he was a brewer for Guinness for a while. He had no real formal training in stats, but as he kind of was working there, they have these huge, this isn't the right word, but these huge like vats that or these like silos where they're brewing the beer. And you don't want, you've got a large quantity and you want to make sure that it's what you're targeting, but you can't test the entire thing. You can only test, small amounts of it, okay? So you would draw out some of the liquid from this huge vat, and you would test to see if it had kind of the properties of the traits of what would end up being, the product of Guinness beer that you were trying to target, right? That target product. So as he was testing these kind of particles, these small amounts from this vat, so these I think what he was actually looking for was like the yeast particles per milliliter in like a little bit of liquid he was taking out, he noticed they followed a Poisson distribution. He didn't really have the words at the time to call it that, but he realized that there's a pretty consistent distribution to these samples that he was taking. Okay, so he leads him to these other important discoveries he comes up with, which a lot of these distributions that we'll start looking at, like the Poisson, right? We've got the Gaussian distribution, and they all are named after who discovered them. Well, because he had no formal training in statistics, they kind of just give those distributions and these findings that he had. Kind of the student T distribution is the one which we'll talk about kind of later on in this course. But no, he didn't get any respect basically, but made a bunch of money. So let's think about an example kind of what he was doing. So there's this huge volume of liquid, right? That's not a time interval, that's like a space interval, right? And so he's drawing 1 milliliter out at a time and looking for the number of particles, I said, yeast cells that are in this liquid. So the sample he takes, he sees that there's 10 particles in this milliliter, right? So that's kind of the average that he sees, right? So what's the probability that the entire liquid actually has a concentration of 8 particles per milliliter? Well, the average that we saw is 10, but that could be a little bit off. So maybe we're thinking about what's the probability it's a little bit lower than that, right? Just because I took this one sample, maybe that 1 milliliter had a few more particles in it, right? So we could use that mean of 10 and that X we're interested of 8, right? So lambda is 10, that's our average that we saw. We want to know what's the probability that that actually has 8, right? Or, I think I set this up a little bit weird way. Think about, I get this sample and it's 10, and that's what I wanted. Maybe I want to, well, yeah, but what's the probability it's actually 8? Because if it's 8, the whole vat is ruined, or something like that, So, you can imagine these are like things that you would, pull product off the assembly line and test them kind of thing. So you plug in that lambda of 10, you plug in that probability of 8, right? And the probability that it's 8 is about 0.11, right? So, if you're thinking about, it's a relatively high probability that this vat actually, even though I tested it, potentially like it isn't what I'm targeting. And if it isn't what I'm targeting, I've got a ruined product that I'm gonna have to eat the costs on. And so maybe if it's as high as 10%, maybe I want to start to think about things like, how do I insure myself against, these bad things happening? So this is a pretty, using the Poisson distribution is a pretty applicable thing when we're thinking about, products and products that need to be certain weights, or products that need to be certain strengths, right? Because if they're not, right, and we can't test every product, but we can pull off, a couple off the assembly line and test them, similar to taking a couple milliliters out of, a huge, I'm guessing thousands of liter vat, okay? All right. Any questions? I feel like I'm kind of going without people like in front of me. Sometimes it's tough. I kind of get going and forget to take some pauses here and there. Okay. Also, I kind of like some of these examples. So here's the Poisson distribution kind of meme. Have you heard the joke about the Poisson distribution? It's pretty funny or fishy. This is because I think Poisson is French or maybe Italian. I forget which one, but it means fish. So I'm going to end today's class with one more example, but next week we'll do the Poisson again. I don't want to do it without being able to write it out for you. I want to show you one more trick we can do with the Poisson starting on starting on Tuesday, and then the rest of Tuesday and next week's class on Thursday, I'll actually just be working through some exam review problems. So those practice exams I posted, if you do get a chance to look at any of them, I'll start with questions that people have. Otherwise, I'll just start probably working through practice exam A problems. After we go over that, kind of one more topic that is related to the Poisson distribution. It's a little bit tricky that I want to make sure I can kind of have something to write. And let me make sure, yeah, the camera's still not picking up here. So, all right. So with some of the stuff that we've talked about before, there's kind of an interesting like little example here. So what's the probability that in a class this size, and I think let me see what I used, just to double check. I think I used, yeah, so I only used 35 people. I think this class, we technically have a few more people than that, but let's assume we had a class of like 35 people. What's the probability that 2 or more people in that class actually have the same birthday? So a couple assumptions. Let's assume we don't have twins, right? Let's assume that every day is equally likely for someone to be born on, right? And that every single person's birth is independent. So we don't have like 2 people in the class where their mothers were, timing their births to be able to kind of have kids around the same time or something like that. So usually if you ask people this question, like what's the probability 2 people in a group of 35 have the same birthday, you would think it's, most people answer A, right? They think it's relatively low. Okay? Or if you think about, how many people would we need? Because, if I have 1 million people, the probability that 2 people have the same birthday is going to be relatively high, actually. So how many people do I need to make it at least a 50% chance that 2 people in that group would have the same birthday? So we can kind of use some of the rules we've talked about. Think about X is the event of people having the same birthday. Well, we can actually find that by 1 minus its complement. So what's the complement of 2 people in this group having the same birthday? It would be that nobody has the same birthday, right? Everybody has an individually, unique birthday in this group of 35 people. So what we can do is start to think about what we can really rewrite this is the probability that let's say we start going sequentially through people. So if I had like everyone in the class lined up, I go to the first person and I say, okay, what's the probability that first person has a unique birth date among the people in this room? Well, I haven't looked at anybody's birth date yet, so their probability is, well, there's 365 days that they could have a birthday on that would be unique, so 365 out of 365. So a probability of 1. Okay, not very interesting. But I go to the second person. Well, what's the probability that they have a unique birthday? Well, now they can't have a birth date the same as the first person, so there's only 364 days. So the probability that they have a unique birthday is 364 out of 365. And then the third person, well, now there's only, there's 2 birth dates I've already looked at, so now there's only 363 days, right, possible for them to have a unique birth date. And this kind of continues all the way, you could kind of write a mathematical, what is this we're really doing here? We're just running all the way down to the 35th person. We would then have the probability that every single one of those 35 people had a unique birth date. Right? Well, if I want to know the probability the first person has a unique birthday and the second person and the third, if these are independent events, I can simply multiply these probabilities by each other and get the probability of the intersection of those. Okay? So I just multiply the probability that every single person has kind of this unique birth date. And actually, it follows a format very similar to that binomial distribution. It's not quite the same, but kind of notice it's almost like the first part, except for we have a little kind of power thing going on here. But it's similar to what we were looking at. But if I multiply all these by each other, and like I said, you can simplify this down to here. Jeez. We get the probability of the x complement is 0.186. You on Zoom didn't hear that, but someone was yelling in the hallway. So 0.186, but remember, that's the probability of the complement. So we still have to subtract that from 1. So the probability that in a group of 35 people, that 2 people have the same birthday is actually 81%, right? Which seems crazy, right? But, it's kind of how it works out. It just kind of goes against our initial intuition. And we can actually back out, if you tried plugging in different values for X here, like the number of people in the room, you actually only need 23 people to just, get right over that 50% mark. So at 23 people, it's about a 50-50 chance that 2 people in that room have the same birthday. So like if you're ever in like a larger group, like of 30, 40 people, the actually safe bet is to bet that 2 people in that room were born on the same day, which I think is pretty counterintuitive, but pretty cool that we can kind of take some of the principles that we've talked about. When events are independent, we can just multiply the probability of each event occurring. So this is the probability each person had a unique birthday. Using 1 minus the complement to find the probability of an event. And I don't know. I just think that's kind of an interesting example. Always kind of like it when a statistics example goes against our basic intuition. So I'll end there. That got out a little bit early today, but that's because I was planning on doing the additional kind of example for Poisson today. But I'll go back to my office. I'll probably even kind of film a little short video. No, actually, you know what? I'll hold off. I'll just wait until we meet Tuesday to do that additional Poisson stuff. So I'll get an online quiz up, though, for today's material. It'll probably be a Poisson distribution example that you'll have to work on. Other than that, make sure you're getting those homeworks kind of worked on, get them out of the way early. We're getting closer. I'll talk more about the specifics of the exam next week on Tuesday's classes as well. Get those homeworks out of the way early so we can start studying for that exam. And if you have any questions, feel free to email me. I've helped more people kind of reaching out. And I know the weather's been bad, but hopefully if I can kind of get us a classroom in the business building, I start seeing a couple more of you kind of in person, because it's always weird not having kind of hardly anyone in front of me to talk to. So stay safe, and I will see you guys on Tuesday.